Hello students. Now here we will see gradually varied flow computations. Okay, why computations of GVF profiles is necessary. So first is need for computation. It is necessary to know the length of a profile up to which it affects the particular profile and changed conditions of flow. Okay, for example, if M1 flow profile occurs on upstream of a dam, and it is necessary to know how far upstream side water levels will be affected and up to what extent. Okay, this is necessary to find out the area being submerged, how much submergence level or depth of water will be there, time of year, that means for what time, how much time of a year it will remain submerged. Okay, and effects of submergence on natural environment, then flood situation, etc, etc. This all I am talking about M1 flow profile, which is on the upstream side of the dam. Next is H3 flow profile. If suppose this flow profile is occurring on the toe of a dam, finding out H3 profile is required to know what length of apron is required to contain the jump. We know apron is constructed to reduce or to minimize the damage caused by uh, shooting flow to the toe of the dam. Okay, this height and length of a jump are required to construct length of a training walls and guide banks. Okay, so these are the two examples to show what is the need for computations of gradually varied flow profiles. Okay, computations means we will be finding out length, depth, etc, etc. Okay, now there are three methods for GVF computations. First is the direct step method, next is the graphical integration method, and third is standard step method. We will see all these three one by one. So first method is step method or direct step method. Okay, so the sketch used to illustrate that method is like this. So this is the datum line. Okay, this is the bottom of the channel, bottom slope S0. This is the top water surface line, SW slope. This is the energy line, its slope will be SF. Okay, section 1 and section 2. We will be considering liquid volume between section 1 and section 2. At section 1, depth of water is y1, datum head is z1, and velocity head is v square by 2g. Okay, this v square by 2g plus y1 combinedly it is called as e1, and this is z1. Okay, on the section 2 side, so this is z2 datum head, this is y2 depth of water. Okay, and this is v square by 2g, distance between top of water level and energy slope, it is v square by 2g. Okay, and this height represents head loss, hf, a horizontal line drawn from here, and when we take this intersect, this is nothing but hf or head loss. Okay, now hf can be found out sf into dx, sf slope of the energy line, okay, and dx this length. Okay, here on this side, this bottom length being considered here is dx. Okay, and s0 is its slope. So this height, okay, z1 minus z2 will be s0 dx. Z1 minus Z2 will be S0 dx, and here difference between energies of section 1 and section 2 is SF dx, and that is equals to HF. Okay, now some theory part of the method. In this method, the length of channel is divided into number of short reaches, and computations are carried out for each step. Okay, the length of channel is divided into short reaches, and one step is equals to one reach is find out at each time, starting from one end to reach the another. Okay, so consider a short reach of the channel of length dx between section 1 1 and 2 2. Dx is very small and can be considered as a straight line. Okay, now applying Bernoulli's equation between section 1 and section 2. So we are familiar with this equation. Z1 plus y1 plus v1 square by 2g is equals to z2 plus y2 plus v2 square by 2g plus hf. Hf obviously the head loss. Okay, so we can write it like this: z1 minus z2 plus e1 is equals to e2 plus hf. I told you already y1 plus v1 square by 2g is nothing but e1, and y2 plus v2 square by 2g is e2. Okay, so z1 minus z2 plus e1 is equals to z2 e2 plus hf. Okay, so but z1 minus z2 is equals to s naught dx and hf is equals to sf into dx. So what equation we get is this: dx plus e1 is equals to e2 plus sf into dx. We are interested in finding out dx, so dx is equals to e2 minus e1 upon s naught minus sf. Okay, so this equation is used in step method. We will be seeing the step method in detail in the next video.